is the sixth week of NPTEL Live classes, live session of Advanced Control System. So today I'm going to discuss about the state transition matrix, then controllability. Then we discuss about the notion of the controllability, and we will see some examples regarding this state transition matrix and controllability. Also, we will also discuss about the Cayley-Hamilton theorem, how we find out the state transition matrix using Cayley-Hamilton theorem. All this, okay. So, so let me share my screen first. My screen is visible to you, right? So, in previous class, we have discussed about state transition matrix. So this is basically a very fundamental matrix, or we can get the fundamental informations about the systems um, through state transition matrix. So we know this is a state transition matrix. We basically define state transition matrix in that format. Or e to the power at, which is basically a plus at plus at square plus factorial 3at cube in this way, right? Now we know that we can find out the state transition matrix using some diagonalization process. In previous class, we have studied about the diagonalizations. So and studied about the few properties of the state transition matrix. So as we know that the one of the property of state transition matrix is A multiplied with e to the power at is equals to e to the power at multiplied with A. So that means this two matrix A and e to the power at, and these two matrices basically commute with each other. So we have shown in previous classes how this is happened. Now we will show this to you, like how using diagonalization process we can find out the state transition matrix. So basically, as we have studied in previous class, that state transition matrix e to the power at is basically the Laplace inverse of Si minus A inverse, right? So here basically we have to find out the Si minus A, the inverse of this Si minus A matrix, and then take the Laplace inverse of this matrix. So if A matrix is diagonal in nature, then it won't be an issue. But if it is not diagonal in nature, then it's difficult to find out the Si minus A. So for that case, what we can do, we know that A is equal to P lambda P inverse, right? So lambda is a diagonal matrix and P is a modal matrix. And if we multiply it with the scalar both sides, what we get? P, since T is a scalar, we can put it anywhere. Okay. Now take an exponential, what we get? P lambda T P inverse. So take an exponential and expand this into a series. So what we get? I plus P lambda T P inverse plus P lambda T factorial 2 P lambda T P inverse into P lambda T P inverse in that way, right? Factorial 3 in that way. So what we get, if we write I in P inverse format, so we get P lambda T P inverse plus half in factorial 2 1 by factorial 2 P lambda T square P inverse in that format. So basically, if we take common P from the left side and P inverse from the right side, we get this structure, right? So this is basically P to the power lambda T P inverse. So basically, so here this term, this is basically a diagonal one. We know that. So we know that lambda is basically in this format, lambda 1, lambda 2, in this format, right? All the diagonal elements are there. Now, if e to the power lambda t is basically very easy to find out, e to the power lambda 1 t, e to the power lambda 2 t, in that way, e to the power lambda n t. Okay. So, therefore, e to the power at is very easy to find out because we know the p matrix, we know how to find out the p matrix is just basically the linearly independent eigenvectors of the matrix, put it in the into the column of p, right? And then here lambda 1 t to the power lambda 2 t, in that way. Sorry, these all are in diagonal, lambda 2 t, lambda n t, and p inverse. So the calculation is very easy. So now we will take an example. So the example is, yeah. So I have a matrix, something like that. I have a system. Let's say x dot equals to, it's a 2 cross 2 second order system. 1, 4, minus 2, minus 5, x plus 0, 1, u, and y is equal to, sorry, 1, 0. If you find any, if you find any problem, you can stop me and ask me the question. Okay. X. So this is basically the second order system, and you have given that the initial value is x0, which is 1, 0. So first question is, find out the state transition matrix using diagonalization, and the second is find out the response of the system. Okay. So this is the questions that you have asked. So now the answer is, so we have to find out the state transition matrix using diagonalization process. Okay. So for the diagonalization process, what should we do? We have to find out the eigenvalues of these matrices. Okay. So the eigenvalue is determinant of lambda I minus a equals to 0, and using this you will find that the eigenvalues are lambda 1 equals to minus 1 and lambda 2 equals to minus 3. Okay. So to find out this p is called over here, this p is called over here is a, p is basically modal matrix and lambda is diagonal matrix. Okay. So to find out the since we have seen in the previous classes that if we have a distinct eigenvalues, so definitely we will get a distinct eigenvector. So we can put all those eigenvector into the column of P, and we will get the modal matrix, right? So it is not in a controllable canonical format. So it is not in a controllable canonical format. So we cannot use the format like 1 lambda lambda square. This format we cannot use for the P matrices. So we have to find out the eigenvectors. So what are the eigenvectors? So eigenvector is, let's say, lambda 1 I minus a into v1 equals to 0. Okay. So what is lambda 1 I minus a? It is lambda 1 is 1 minus 1 minus a 1 4 minus 2 minus 5 into v1 1 v1 2, we get 0 0. So what we get over here is a minus 2 minus 4, 2, and plus 4. So what we get? So V1 is basically 1.5. Sorry, 1 minus 0.5. This is one eigenvector corresponds to lambda 1, and then eigenvector corresponds to lambda 2 is lambda 2I minus a V2 equals to 0, which gives us minus 300 minus 3, and here 1 4 minus 2 minus 5. So V21, V22, this is 0 0. What we get, it's a minus 4 minus 4 minus 2 plus 2 2 V21 V22. We get, so V2, what V2 we get, it's basically 1 minus 1. Right? So this is the value that we get. So we know that A equals to, so P matrix is basically put the column, put the eigenvectors in the column of the P matrix. So what we get, 1 minus 0.5 and 1 minus 1. So this is linearly independent, so we can find out the P inverse of this matrix. Okay. So we know that A equals to P lambda P inverse. Okay. So definitely lambda equals to P inverse A P, right? In this format. So if you multiply the P inverse 1, sorry, 1.5, 1 minus 1, this inverse, then 1 4 minus 2 minus 5, and then 1 1 minus 0.5 minus 1. If you do this, you will get that the lambda matrix is in diagonal format. Okay. Now, as we have seen earlier, e to the power at is equal to p e to the power lambda t p inverse. This is the thing that we have get in the previous class. Sorry, in right now. So 1.5 1 minus 1, and this is e to the power lambda t, so it would be e to the power minus t 0 0 e to the power minus 3t. It's very easy to find out the diagonal. And what is the P inverse? So the P inverse of this matrix, so if you find out I'm just finding out the P inverse over here. So determinant is 1 by, it's a minus 1 plus 0.5, which is a minus 0.5, and adjoint is minus 1 minus 1 0.5 1. So what we get 2 2 1 minus 2, sorry, minus 1 minus 2. So this is the P inverse. Okay. So 2 2 minus 1 minus 2. So what we get, if we multiply these three things, we get 2 e to the power minus t minus e to the power minus 3t, 2 e to the power minus t minus 2 e to the power minus 3t minus e to the power minus t plus e to the power minus 3t, and minus e to the power minus t plus 2 e to the power minus 3t. So the first question that you have asked, that find out the state transition matrix, you have find out the state transition matrix using. So this is basically your state transition matrix. Okay. So now the next question that you have asked is to find out the response of the system. So for a force system, that is x dot equals to ax plus bu, this is a force system because you have to apply u externally, right? the system is not driven by its initial condition, so it's a forced system. So for that case, we know the system's response. What is the system response? It's a e to the power at x naught plus integration 0 to t e to the power a t minus tau b u of tau d tau. So you have studied this in previous class. So I know the value of e to the power at, and I have to find out this term. And u that you have asked over here is the u. My mistake, just mention like, so u is considered over here is a step input. Okay. So ut is basically 1. That is a step input. So what should we do? So xt equals to, put the value of e to the power at over here. So 2 e to the power minus t to minus 3t, and x0 you have given is 1 comma 0. This is e to the power at into x0 plus integration 0 to t, now e to the power a t minus tau. So in place of t, you have to replace it with t minus tau. E to the power minus 3 t minus tau, e to the power minus t minus tau plus e to the power minus 3 t minus tau, 2 e to the power minus t minus tau minus 2 e to the power minus 3 t minus tau t minus tau plus 2 e to the power minus 3 t minus tau. So this is e to the power a t minus tau into b. What is b? B is 0, 1, and you know that u tau is basically 1. So this is the equation. So xt is basically what you will get. You will get 2 e to the power minus t minus e to the power minus 3t, and this is minus e to the power t plus e to the power minus 3t. Multiply these two terms, and here you have to separate the t term and tau term. You have to separate the t term and tau term, so that first you just multiply this 2 e to the power minus t minus tau e to the power minus 3 t minus tau minus e to the power minus t minus tau plus 2 e to the power minus 3 t minus tau. You multiply this term with this term, and you get this, right? And this is d tau. So I'm just integrating with tau, not t. So t is basically considered as a constant term. So we just integrating only t term over here. We can integrate each term separately. Okay. So this is integration 0 to t 2 e to the power minus t into e to the power tau d tau minus 2 0 to t e to the power minus 3t into e to the power t tau d tau, and here minus 0 to t e to the power minus t into e to the power tau d tau plus 2 0 to t e to the power minus 3t into e to the power 3 tau d tau. So this is basically 2 e to the power minus t into, this is e to the power tau. E to the power tau is basically e to the power t minus 1, because e to the power 0 is 1. Here minus 2 into e to the power minus 3t. Now integration 3 is over here. It should be e to the power 3t into minus 1. This is minus e to the power minus t, e to the power t minus 1 plus 2 by 3 e to the power minus 3t, 3t minus 1. Right. So finally, what you get, you will get, if you add and subtract these two vectors, and you will get e to the power minus 3t plus 1/3 e to the power minus 3t. Okay, so this is basically your xt, and now we are asked, the question is basically the system response. So yt is basically c, which is 1 0 into xt. Xt is 4 by 3 minus 1/3 e to the power minus 3t minus 1/3 plus 1/3 e to the power minus 3t. So this is basically 4/3 1/3 e to the power minus 3t. So this is your answer. So in that way, if you find out the state transition matrix using the diagonalization process, you will get the calculation is very much easier than the previous one. Now we move to the Cayley-Hamilton theorem. So, just let me ask you one question. So, is there any doubt in this numerical? So, I guess you have no doubt.
No.
So, I'm just, you have no doubt, right?
Yes, sir.
Okay. So, I just move to the next Cayley-Hamilton theorem. Uh, so, Cayley-Hamilton theorem says that every square matrix satisfies its characteristic equation. So, if a, this is basically a layman style, I have just said the theorem. I'm not going to in details. So, if A is a square matrix, so its characteristic equation, let's say P, this is its characteristic equation, let's say lambda to the power n plus a n minus 1, lambda to the power n minus 1 plus up to, let's say, a0, or a lambda plus a1 lambda a0. This is the characteristic equation. Then this is equals to basically 0, right? So the Cayley-Hamilton theorem says that if we put a over here, it will also satisfy this equation. That means a to the power n plus a n minus 1, a to the power n minus 1 plus a1 a plus a naught I. This is also equals to a 0. This 0 is basically a matrix with all elements 0. And here 0 is basically a scalar. Okay. So I just deepen the things. So since this is a scalar term, so this 0 is a scalar, this is the matrix term, that's why here I is included over here, and this is a matrix. This 0 defines that all the elements of this matrix is 0. So using this Cayley-Hamilton, using this Cayley-Hamilton theorem, we can find the state transition matrix, or you can say the inverse of a matrix, or in previous class we have seen that, let's say, in previous class we have seen that, let's say you are asked to find out the value of a to the power 100. Okay, so it is very difficult to find out the a to the power 100, because we have to multiply 100 times, multiply a 100 times, right? So it is difficult. But using state transition matrix, using diagonalization process, we find out the a to the power 100 very easily. So you can see the examples in previous class notes. So similarly, we can find out this higher powers like a to the power 100 or a to the power 50, we can find out this kind of things using Cayley-Hamilton theorem as well. Okay, so we just need an example for that. So I'm just doing this example on 2 cross 2 matrices. Okay, so Cayley-Hamilton theorem also says that if just a minute, yes. So Cayley-Hamilton theorem also says that any polynomial, it also says that Cayley-Hamilton theorem, if let's say f lambda is any polynomial in lambda, then there exist, let's say, beta naught, beta 1 up to beta n minus 1. There's a coefficient belongs to, let's say, real number such that f of a is equals to beta naught I plus beta 1 a plus up to beta n minus 1 a to the power n minus 1. Okay, so this Cayley-Hamilton theorem also says these things, and also it also says that if if f lambda be any polynomial in lambda and p lambda be the characteristics equation, then there exist two unique polynomials g lambda and r lambda which satisfy this following equation, which is f lambda is equals to p lambda into g lambda plus r lambda. Okay, so using this formula, we try to find out the, let's say, next questions what it asked. So next example is given. So a is equals to 1 0 1 2. Okay, find out a to the power 37. Okay, one approach is you can multiply a 37 times and you will get the answer, which is very cumbersome process. The next process is using diagonalization. You can do that. Now here we will see using Cayley-Hamilton theorem how we can solve this problem. Okay, so first of all, we just find out the eigenvalues of this matrix. What would be the eigenvalues? It is, so definitely it's lambda minus 1 0 minus 1 lambda minus 2. So we will get lambda minus 1 lambda minus 2 equals to 0. So therefore lambda 1 equals to 1 and lambda 2 equals to 2. Right, this 2 is the eigenvalue. So now we know that p lambda, the characteristic equation, this p lambda is 0. So therefore f lambda, what is the equation? G lambda plus r lambda. So this p lambda is 0. So we will get that f lambda is r lambda. And also we have seen that if f lambda any polynomial, if f lambda is any polynomial lambda, then there exists this term where f a will satisfy this equation, right? So we know that f a equals to what should be b naught I plus b1 a, but we don't know the value of b naught and b1, so we need to find out the value of b naught and b1. So what f a you are asking over here? So here f of a is basically a to the power 37, right? So that means a to the power 37 is equals to beta naught I plus beta 1 a. Okay, so we can do that. Lambda 1 to the power 37 is equals to beta naught plus beta 1 lambda 1. So lambda 1 is 1. So basically beta naught plus beta 1 is equal to 1, right? And then lambda 2 to the power 37 is equals to beta naught plus beta 1 lambda 2. So what we got? Beta naught plus 2 beta 1 is equals to 2 to the power 37. Okay. Now this is equation, let's say 1, this is equation 2. Solve these two equations. What we get? We get beta 1 equals to 2 to the power 37 minus 1, right? This is we got beta 1. Yeah. And beta naught, put this beta 1 value is any of this equation and you will get beta naught, which is 2 minus 2 to the power 37. Okay. So now you know the value of beta naught. So you can find out the A37, which is beta naught I plus beta 1 A, right? So beta naught means 2 to the power 37 minus 1, 1001 plus beta 1 is 2 minus 2 to the power 37 into A. What is A? 1012, right? So put the value over here, 2 to the power 37 minus 1, 0, 0, 2 to the power 37 minus 1 plus 2 minus 2 to the power 37, 0, 2 minus 2 to the power 37 and 2 into 2 minus 2 to the power 37. I think I'm doing right. Yeah. Now do the calculations. What do you get? You get this is 1, this is 0, this is 2 minus 2 to the power 37, and here we'll get 2 square. Let me just see, this is 2. Okay, sorry, I made a big mistake. This is beta naught is 2 to the power 37 and this is beta 1, which is 2 to the power 37 minus 1. So this should be 2 minus 2 to the power 37, 2 minus 2 to the power 37, and this is 2 to the power 37 minus 1, and this is 2 to the power 37 minus 1, and this should be 2 to the power 38 minus 2. Yeah. So this is anyhow this is 1. Okay. This is 0. This is 2 to the power 37 minus 1, and this term is basically 2 to the power 37. So this is your a to the power 37. Now in using calculator, you find out the 2 to the power 37 value and put it over here. So this is a to the power 37. So this is way more easier to multiply, easier than multiplying the 37 matrices, 37 A matrices multiply with each other. So this is basically the matrix find out using Cayley-Hamilton theorem. Now the next example, the state transition matrix using Cayley-Hamilton theorem. Okay. So if you find any difficulty to understand, you just stop me anywhere. Okay, so that I can explain whatever. So what's the matrix that is given to you? This is A equals to -1, 1, -1, 1. This is the matrix that is given to you, and you have to find out the e to the power 80. Okay. So for that case, what should you do? You first find out the eigenvalue of this matrix, right? So as you see over here, by checking this matrix without doing any one, you can say the one eigenvalue. Can you sorry? You can say the one eigenvalue over here because you see that these two rows are equal. So definitely, if we take a determinant of this matrix, definitely it will be equals to 0. So if any matrix, the determinant of any matrix is equals to 0, that means at least one eigenvalue of that matrix is 0. That means this matrix is positive this matrix is at least, I can't say about the positive or negative. It's basically using determinant, it's basically 0. That means semi-definite. It's not exactly definite one, right? So whether negative or positive, that you can check, there's a procedure over there. So that means without knowing, without doing that determinant of lambda I minus a, we know that the one lambda is equals to 0. Now you have to see, is there any other distinct eigenvalue or not? Okay. So if we find out the determinant of lambda I, so it is lambda plus 1 minus 1, 1, lambda minus 1. So this is lambda square. So lambda plus 1, lambda minus 1 plus 1. What we get? This. So this is means a square minus b square. This is equals to 0. So what we get? The lambda square equals to 0. That means both lambda 1 equals to lambda 2 equals to 0. Okay. So that means we have a repeated eigenvalue, and the eigenvalue is basically 0. So we know that at least one eigenvalue would be 0 using that, and we see that the next eigenvalue is also comes out to be a 0. So first, using the previous equations, what do we have to do? So f of lambda 1 equals to, let's say, r lambda 1. Okay. So what are over here? So f of lambda 1 is, what is f of lambda 1? It's e to the power lambda 1 t. Because you have to, f of a is basically e to the power at. This is what you asked to find out, right? So that means f of lambda 1 is basically e to the power lambda 1 t. This is equals to r lambda 1. So r lambda 1 is, what is r lambda 1? It is, let's say, beta naught plus beta 1 lambda 1. So lambda 1 is 0. So what we got from here, beta naught is equals to 1, because e to the power 0 is basically 1. So we get 1. And then how to find out, since this is a repetition. So if we find out similar procedure f of lambda to r lambda 2, we will also get beta naught equals to 1, right? Because lambda 2 is also 0. So for that case, what we have to do, we have to take a derivative. So to find out the beta 1, we have to take a derivative of, with respect to lambda of f lambda at lambda equals to lambda 2, then derivative of r lambda with respect to lambda at lambda equals to lambda 2. So what we got over here, this is, let's say, lambda 2 e to the power lambda 2t, sorry, I did a mess because I'm derivative with respect to lambda, not t. So definitely t e to the power lambda 2t is equals to beta 1, right? So lambda 2 is basically, what is lambda 2? Lambda 2 is basically 0. So beta 1 we got t. So what we get, we know that f of a equals to beta naught I plus beta 1 into a, right? So beta naught is 1, I is 1001 plus t into what? Minus 1 1 minus 1 1. So what is the state transition matrix? 1 minus t, t minus t, t. So here we get the 1 plus t. So here we get the e to the power at using Cayley-Hamilton theorem, right? So is it clear? This is clear to you, right? So now move to the next segment. So, so you know the MATLAB commands, right? How to transfer from state space to state space to transfer function to state space. What are the MATLAB commands are there, and how to find out the eigenvalues, and what command we should use to find out the eigenvalues of a matrix. You know that, right? Hello. Okay, so I'm assuming that you know those commands in MATLAB. So I'm not discussing about those commands. Let's move to the next segment, which is the controllability. Okay, so sorry. So just let me discuss about for a discrete time system, because already you have already seen the lecture videos where you have seen how to how for a continuous time systems the controllability matrix comes. So I'm just here. I'll give a brief introduction of a for a discrete time system case, and then we will do some examples. So first of all, what controllability means? How can we? I mean, what is the basic definition of a system is controllable? Do you know what is the basic definition of the controllability, or the system is controllable? How do you define it? Okay. Okay. So basically, the concept is, now if there exists a input, control input, which can transfer a system from x0 to x1 with a finite time. So a system is said to be controllable if there exists a control input which can transfer the system states from initial condition x at t0 to x at t1 within finite time, or rather it's basically defined as a x0 to x1 at finite time t1. So basically this is, if this is x0 and let's say this is x1. So if there exists a control input which transfer the system state from here to here within finite time. It's not that the time is taking infinitely many, infinite time is taking to reach x1. No. So you have to reach there from x0 to x1 within a finite time. So this system is said to be a controllable. Okay. So for, let's say we have a discrete time system. Okay. So at k equals to 0. At k equals to 0, what we get? X1 equals to a of x0 plus b of u0, right? At k equals to 1, what we get? X of 2 equals to a of x1 plus b of u1. So that means a square, put the value of x1, put the value of x1 over here. So what we get? We get a square x0 plus ab u0 plus b u1. Similarly, if we continue in this manner, let's say at x, sorry, k equals to n minus 1, let's say we reach to the final point, which is I'm defining as a xn, which is x1 is basically a to the power n x0 plus a to the power n minus 1 b un minus 1, oh sorry, u0 plus, continue this way, plus a b u n minus 2 plus b u n minus 1, right? Now if we do these things, x1 minus, let's say, a to the power n x0, so what we left out? So a to the power n minus 2 b u1 plus, let's say, a b u n minus 2 plus b u n minus 1, right? So we can write these things in that format, right? b ab a square b up to a to the power, or let's say a square को नहीं लिखते, a to the power n minus 2b, a to the power n minus 1b, and we can put it down over here. It's u naught, sorry, u n minus 1, u n minus 2, then u1 and u naught. So we basically say this matrix as a controllability matrix, right? I'm writing it a cursive C. Okay. So that means x1 minus a to the power n x naught equals to C into, and I'm writing this big term as a big U. Okay. So that's why if this is a state, if this one is a this one is basically a state. If x1 is a state to reach, x0 is the initial state. So using the equation, we can say that if this C matrix, if this matrix is non-singular, that means if this matrix is, or rather it says that if it is a full rank matrix, non-singular is not a right way to say this. If it's a full rank matrix, then we can say the system is controllable. So we will see we will see a few example and why I say this it's a not non-singular is not a right way to say these things. So the first question is example. So linearized, you have given a linearized satellite model. You have given a linearized satellite model, okay, which is x dot equals to 0, 3 omega square, 0, 0, 1, 0, 0 minus 2 omega, 0, 0, 0, 0, and this is 0, 2 omega, 1, 0, x plus 0, 0, 1, 0, 0, 0, 0, 1. So this is basically a linear satellite model is a non-linear. So here is a linearized satellite model where you are given that UR is radial thruster and UT is tangential thruster. So these two are the input to the system, this satellite model. And now the question that you are asked basically, is the system controllable or full state controllable if the radial thruster fails. That means if UR is 0, if UR becomes 0, let's say suddenly the radial thruster of the satellite system is not working, still we can control the satellite or not. And the next question that you have asked is the system controllable if the tangential thruster fails? That is UT equals to 0. So we have to check one by one. If UR equals to 0, can we control the system? That means is the system controllable? If UT is 0, still the system UT is 0 but UR is working. Will the system be controllable at that time or not? We have to check. So let's go to the answer. So okay. So one thing that I forgot to put over here, you are given that even omega equals to 1 radian per second. Okay. The angular velocity is basically 1 radian per second. So put the value of omega over here, what we get, since it's a 1 So it is not that much difficult. So it's 0, 3, 0, 0, 1, 0, 0 minus 2, 0, 0, 0, 0, and 0, 2, 1, 0. This is a matrix, right? So first I'm going to do that, consider as u r equals to 0. That means system has no radial thruster. So if u r equals to 0, so now the B, you can see here over here that the B is the multi, this is basically a multi-input system. There is no one input, there is a two input. So I'm asking over here that if one input fails and system is work with the other input, whether the system will be controllable or not. So first is UR is 0. So since UR is 0, so what would be B? So B is basically only the second column, right? Because first column is corresponds to UR and second column is corresponds to UT. Okay. So now we have to find out AB, A square B, A cube B, and then put it into the column of C, and we have to check that whether the C matrix is a full rank matrix or not. Okay. So we have a B, we have now we have to find out AB. So A is what is AB? This is 0, this is 2, this is 1, this is 0. What would be A square B? A square B is basically A into AB, right? So 0, 3, 0, 0, 1, 0, 0, minus 2, 0, 0, 0, 0, 0, 2, 1, 0 into AB. What AB? 0, 2, 1, 0. And what is the value? It's first is 2, second is 0, third is 0, fourth is minus 4, right? Then A cube B is basically A into A square B. So we know that A 0, 1, 0, 0, 3, 0, 0, 2, 0, 0, 0, 1, 0 minus 2, 0, 0, and A square B 2, 0, 0, minus 4, right? So therefore, its first term is 0, second term is 6 minus 8 is minus 2, third is minus 4, and fourth is 0. Okay. So the controllability matrix, what is controllability matrix? This is C, which is put B, AB, A square B, A cube B, and check B is 0, 0, 0, 1. Then what is 0, 2, AB is 0, 2, 1, 0. A square B is 2, 0, 0, minus 4, and it's 0, minus 2, minus 4, 0. Now, how to find out this matrix is full rank matrix or not? So there is a two way to find out this. Since it's a square matrix, because every time you will not get a square matrix. Let's say how we every time you will not get a square matrix. Let's say this is a multi-input system. Okay, you have a square matrix A and you have a rectangular matrix B. Now, since here I have asked that you have to find out the controllability of the system if UR fails. That means this B matrix now become a vector. Okay. So therefore, you will get ultimately you will get the C matrix is a square matrix. So if I ask that just this is a system and I have to find out the value, find out the controllability of the system. So I did not say that UR is 0, find out the controllability for UR is 0 or UT is 0. I did not say that. I said that both radial thruster and tangential thruster both are working and find out the controllability of the matrix. So in that case, what would be your B? Your B in that case, I'm just writing down and I'll wipe it off. So in that case, your B will be two column, right? Your B will be C matrix will be B1 and B2, two column. Then AB, you have to find out AB. So it would be AB1 and AB2, two column. Then A square B1, A square B2, again two column. Then A cube B1 and A cube B2, right? Again two column. So this is now you have a rectangular matrix, and for a rectangular matrix you cannot find out the determinant, right? So in that case you have to check if this is, let's say, if this is M cross N matrix, okay, and M is less than or equal to N, then of M rank of C always less than or equals to M. It always be a less than or equals to M, because the maximum rank of this C is always be M. It cannot be more greater than N, because M is the smallest number over here. This between M and N, M is the smallest number, right? If both UR and UT in working condition. Is it clear to you why you cannot find out the determinant for determinant of C matrix always? Is this thing clear to you? Miss Vaishnavi, is this clear to you? Okay. So that's why you have to, the proper thing to say is, we have to find out that whether the C is a full rank matrix or not. Okay. So now here you can find out the determinant. So in our case, you can find out the determinant, because this is the C is a square matrix, and you can check whether it is working or not. Or there's another way by which you can find out the rank of a matrix. Zero, that is a Gauss elimination method or row elimination method. You can say this is a row elimination method. So this is the original C matrix. Okay, now you have to find out, you just doing the row elimination method. What row elimination method you are doing? R3 minus 0.5 R2. So I'm changing the R3 by this term. So 0, 0, 2, 0. R2 is 0, 2, 0 minus 1. And this is become 0, R3. This minus, so 1. So this is 0. This is 0. This is 1. Minus 4. Minus 4 plus 1 is minus 3. Is 1, 0. Minus 4, 0. Okay. So next row elimination, what would be the next row elimination method? I'm just showing it over here, is R4, let's say R4 plus 2 R1. I'm changing this R4 term. Okay, 0, 0, 2, 0, 0, 2, 0 minus 2, 0, 1, 0 minus 3, and R4 plus 2 R1, right? So this is 1, 0, 0, 0, 0. Okay. What is the next is changing R2 is basically R2 minus 2/3 R2. I'm changing this R2 minus, oh, sorry, this should be 0. This should be 0. R2 minus 2/3 R3. So this is 0 0 2 0. This is 0. R2 change कर रहा हूँ. So I'm changing this R2. So this is 2 2/3 minus 0 0 0 0 0 minus 3 1 0 0 0. So finally we reach to this matrix. Okay. So now we can't do any more eliminations of rows, because you see that every column, sorry, you see that every column has a non-zero element, at least one non-zero element. Every column has at least one non-zero element, and now you can't do any row elimination process. So that means, since this matrix we cannot find any rows or columns which is completely zero over here. So that means the rank of C is 4 over here, which means full rank. That means system is controllable. Okay. Now if you see, now the next thing is UT is 0. So if UT is 0, if UT is 0, what will be the B matrix? The B matrix would be, the second column is not appear, only the first column appear, which is 0 1 0 0. So this is the B matrix, and now you have to find out AB, A square B, and A cube B. You have to find out AB, A square B, and A cube B. Then you will see that the C matrix that you will get, if you put all this vector in a C matrix, you will get. So you see that this matrix is not controllable. This matrix is not controllable. Sorry, this matrix is singular. This matrix is singular. That means not full rank. So that means, if if the system, if the linearized satellite system, if the for case of linearized satellite system, if the tangential thruster stops working, the system will not be a controllable system. But if radial thruster stop working, still we can control the system. So I suggest you to please verify for this question, check and verify it. Now we move to the next segment. I mean, not next segment. Okay, let's say there are another. So there are another process by which we can find out the controllability of a system. So this is basically a Kalman decomposition method, as we know. So next is Gilbert's method to check the controllability. Okay. So till now, do you have any kind of query? Am I perfectly audible, right? Okay, so I assume that you do not have any query. So I just move to the Gilbert's method to check the controllability. So uh, in Gilbert's method basically use the diagonalization process to check the controllability. So what it does basically, it does like, as we have seen, that A equals to P lambda P inverse. Okay, so for x dot equals to AX plus BU. Okay, if consider X equals to, let's say, P of Z, so what we get, PZ dot equals to A PZ plus BU, right? So Z dot equals to P inverse A. This implies lambda equals to P inverse AP. P inverse AP Z plus P inverse BU. So that means Z dot equals to, let's say, lambda Z plus B tilde U. So this is the new transformation system. This is basically a new transform system. Okay. Now Gilbert method, it says that this lambda, what is this lambda? This lambda contains lambda 1, lambda 2, let's say up to lambda n. If there is a distinct eigenvalue, right? If there is a distinct eigenvalue, if the system have, if matrix A has distinct eigenvalue, then the lambda is in this structure. Then all the off diagonal elements are zero. And Gilbert says that if for each row of B tilde, each row of B tilde is non-zero. Each row of B tilde is non-zero corresponding to each eigenvalue, then the system is controllable. That means for lambda 1, I'm considering a single input over here. So corresponding lambda 1, if B1 is non-zero, then then this particular state is controllable. Then lambda 2, B2 is non-zero, then this particular state is controllable. In that way, if all the elements of B, all the elements of vector B in case of single input, I'm just mentioning in case of single input, if all the elements of the vector B is non-zero, then the system is controllable. In case of multi-input, at least there exists one non-zero element. Okay, we will see in a few examples. Okay, but it is not always, we never get a diagonal form always, because we have system have a repeated eigenvalues, and because of these repeated eigenvalues, we have there's a possibility that we do not get multiple eigenvectors for a single eigenvalue. For a repeated eigenvalue, we do not get a multiple eigenvectors. So that's why the algebraic multiplicity and geometric multiplicity, these two are not equal, that we have studied before. So that's why we have to find out the generalized eigenvector, and we never get this kind of structure. In that case, in case of repeated eigenvalue case, sometime we get this structure, Jacobian structure, z dot equals to z jz plus p tilde u. So let's say lambda 1, lambda 1, 0, here 1. Then let's say lambda 3, lambda 3, here 1, 0. And then let's say lambda 5. I'm considering a 5 cross 5 system. So this is 0, 0, March 20. So you can see, or rather I use grid. So this is one Jordan block, this is another Jordan block, and this is another Jordan block. So if this kind of structure arise, in that case, what would be the condition? The condition would be, since here you can see distinct eigenvalue, here you can say distinct eigenvalue is lambda 5. So corresponding this line Bn should be non-zero element. And here you can see corresponding to lambda 3, you see a Jordan block over here. So the last row of this Jordan block, corresponding to the last row of this Jordan block, here the B should be non-zero. And for this case, this is the Jordan block corresponding to lambda 1. For this case, the last row of this Jordan block, this B2 should be non-zero. Okay. In case of multi-input, at least one non-zero element should exist. So why is this things? Because if you see this, let's say if you Z1, let's say I have a 2 cross 2 system and it's a diagonal, let's say lambda 1 0 0 lambda 2 Z1 Z2, this is dot, and this is, let's say, B1 B2, and this is B. So you can see this Z1 dot is basically Z1 plus B1U, and Z2 dot is basically Z2 plus B2U. So that means this U should be there. U should be there in first case to control the state 1. And here U should be here in the second case to control the state 2. There is nothing like a state 1 is controlled by state 2, right? In case of Jordan block system, let's say, why these things happen, if let's say it's a lambda 1 1 0 lambda 1, this is the case, let's say, and this is b1 b2, and here I have said that, so the question is, so the equation is lambda 1 z1 plus z2 plus b1u, and this is lambda 1 z2 plus b2u. So in this case, we need a control input. We need, at least we need a control input to control the Z2. Then this control Z2 basically control the Z1. So in that case, if let's say if B1 is 0, still the system is controllable because I'm applying a control input and B2 is non-zero. Let here B1 is 0 and B2 is non-zero. Then what should it do? It does that this non-zero control non-zero input control the state Z2, and this control Z2 indirectly control the state Z1. So that means the whole system is controllable. Okay. So at least there has to be a one control input to the Here in this case, there has to be one control input to the system state Z2 so that it can control the system Z1. So let's see a few examples. Is this logic understandable to you, Ms. Vaishnavi? Hello, am I audible? Hello.
Hello.
So yeah. So am I
Yes,
audible, right?
yes, sir.
So is the logic of this Gilbert method to check the controllability is, I mean, understandable to you? Is it
Yes,
okay?
I got it. Yeah.
So just I'm just showing you some examples. So the examples one. So let's say the system that you have given is like that. So this is multi-input case. Okay. So what Gilbert says that corresponding to every eigenvalue, if at least there exists one non-zero element in B. Okay. So in case of this eigenvalue 1, we have a non-zero element, at least one non-zero element. That means let's say this U is something like that. Let's say U1, U2. So for this eigenvalue, I have at least U2 to control this state. For this eigenvalue, I have at least U1 to control this state. And for this eigenvalue, I have U1 and U2 to control this state. So Gilbert says that controllable, or rather say state controllable. So next is, so normally what you have to do, you have to give, basically you are given a system and you have to find out its diagonal form using this diagonalization method. Using this diagonalization method, you have to find out the diagonal form and then check those conditions satisfied or not. So here I have just showing you only the diagonal form over here. Okay. So in exam, you may ask to find out the diagonal form at first and then check the controllability. Okay. So the next system is x dot equals to, this is minus 1 1 0 minus 1 0 0 0 0 0 0 minus 2 1 0 0 0 minus 2. This is 0 0. This is 1 0. This is 0 1. This is 0 0. So here you can see there is a two Jordan block, right? One corresponding to lambda equals to minus 1 and another Jordan block corresponding to lambda equals to minus 2. That's why the system matrix is not completely diagonal in format. So what Gilbert says, the last row corresponding this last row, there exists at least one non-zero input. There exists at least one non-zero input. That means these two states are controllable. We can control these two states. Now next, we can see there is a control input corresponding to first row, but there is a no control input corresponding to second row because all the element column elements are 0. That means we cannot control the last state. That means x4. That state x4 we cannot control because there is no control input exist. Though their control input exist over here, but this can control the x3, cannot x4. But if, let's say, if this term is 0, if we put this term is 0 and this term is 1, then we can say the system is controllable because this control input control the system x4 and this controlled x4 control the system x3. Okay, but this is not the case. The case is this is 1, this is 0. So according to Gilbert's method, the system is not fully controllable. Okay, so these are all the examples. Now move to new examples. So this is regarding the Gilbert's method. Okay, now move to the new example. Okay, so the example is, okay, so you have given a discrete time system. Let's say x k plus 1 is equals to 1 1 0 0 1 0 and 0 0 1. Xk plus 0 0 1. Okay, so this is the system that you are given and you are asked that, let me put it in that format. So is x1 322 reachable, and if yes, what minimum steps required? Okay. So first, what should we do? Well, we first check whether the system is controllable or not. So the matrix A is reachable, initial state x0, let's say 0 0 0 is given. Okay. So 0 0 0 1. Okay. So this is A and B is 0 1 2. Oh, sorry, 0 1 1. Okay. Now I have to find out the AB. AB is A multiplied with B. A multiplied with B, what is 1? Yeah, this is 1 and this is 1. AB, and A square B is basically A into AB, right? So A multiplied with AB. So this AB is over here. So this is 2 and then 1, then 1. Okay. So the C matrix is 0, 1, 1, 1, 1, 1, 2, 1, 1. So either you can find out the determinant of matrix C or you can do the row elimination method. But before you do anything, you just check that these two rows, this one and this one, these two rows are similar. That means if we do the row elimination method, we get the one row completely zero. If we do that row elimination method that we have done in the previous question, we get that this one row is completely zero. That means this matrix is not a non-singular matrix. So if you find out the determinant of this matrix C, you will get the determinant is zero. So that means system is not state controllable. So that means, is that mean we cannot reach to this state from here? Is that means that we cannot reach to x0 from x1? No, this is not the case. If system is fully controllable, that means whatever the value of x1. So let's say if the system is, the diagram should be, if the system is, let's say, fully controllable, this is, let's say, x1, x2. I'm talking about the two-dimensional system. If the system state is fully controllable, then we can go any state from zero. We can go any state from zero. No one can stop it. We can go any state from zero, right? But if the system state is not fully controllable, that means we can go to few state. We can't go to the whole. We can't explore the whole state space. This is basically a whole state space. If the system state is fully controllable, the system can explore the whole state space. But if system is not fully controllable, system cannot explore the the whole state space. It may explore, let's say, it may, if the system is not fully controllable, that it's possible that it may explore only this portion, or it may explore only this portion, or it may explore only this portion, or only this portion, or maybe it can explore only this portion, or it can explore only this portion. That means only few portion that can system can explore if the system is not fully controllable. There is a little weaker notion of that is stabilizability. The controllability is a very strong notion of a system controllable or not, but there is a weaker notion of stabilizability, which I'll go to the next part. But before that, I just solve this question. So what you have asked is the system is not state controllable, right? But still, let's see, we can still go to the state or not. So what the reachable state is 3, 2, 2. This is basically the final state information. So now check, since we have given a discrete time system, so check the next time step. What we'll get? A x0 plus b u0. X0 is 0, 0, 0, 0, 0, right? So this term is 0. So what we'll get? Because x of 0 is, this is given. So this is become b into u of 0. So what is b? 0, 1, 1, u of 0. So we do not know what u we can choose. So that means obviously my system state is 3, 2, 2, and here exists as 0, 1, 1. So we can put any u, we cannot reach to the state. Okay. So let's go to the so there exists no u naught which leads x of 1 to 3 to 2, right? Now check next time step x2, which is basically a of x1 plus b of u1. So what is a of x1? A is 1 1 0 0 1 0 0 0 1, and x1 is basically this term 0 1 1 u naught plus 0 1 1 u1. Okay. So now what is the value of this term 1 1 1 u naught plus 0 1 1 u1? So that means what you will get, this is u naught, this is u naught plus u1, and this is u naught plus u1. So that means if we choose here, if we choose u naught equals to 3 and u1 equals to -1, then what will happen? 3 3 minus 1 and 3 minus 1 will reach to the state 3 to 2. That means there exists a control input which is u naught, uh, 3 minus 1. So there exists a control input which leads the system to this state in 2 times step. Okay. So this is basically, sometimes you may ask that okay, system is not controllable, so you just check, okay, first check, so you basically ask that whether this state is reachable or not, and you check the system is not controllable and you say that no, this state is not reachable. So this is not the right answer. So you check whether the system state is reachable or not. Full state controllable does not mean that we cannot go to any state. We have to check whether this system can span this state or not. So this is the one example. Another example of, okay, so before that I just talk about stabilizability. So stabilizability, as I've said before, this is basically the weaker notion of controllability. You have already studied in the lecture video. So it says that, let's say, as you can see, the system is not fully controllable. Sorry. Where? Okay. The system is, as you see, as you have seen, that system is not fully controllable, right? In this case. So now you have check first whether the controllable input, sorry, whether the stable modes are, uh, let me put it in that way, whether the unstable mode are controllable and those are non-controllable state, non-controllable modes are stable or not. What does that mean? So it says unstable modes are controllable and non-controllable modes are stable. So what are these modes? Modes means eigenvalue. Okay. So in that case, I'm not discuss the whole things. So the basic thing is, if you see in case of a diagonal system, this is this is the diagonal system. Okay. So in that case, in case of diagonal system, the eigenvalues lies in the diagonal. Uh, in the in all this is the lambda one, this is lambda two. So this, let's say lambda one is unstable mode because this lambda one lies in the right half of the complex plane. This two, this is right half of the complex plane. This is unstable mode, and this is stable mode. So if this stable mode, there is a no control input, this may not be the system state, may not be the fully controllable, but it is stabilizable because eventually this state this state basically reaches to 0, because we know that e to the power minus lambda to t is tends to 0 at as t tends to infinity, right? So this stable mode is basically converged to the 0, whether this is a there is a control input or not. And since this e to the power lambda 2t, because lambda 2 is negative, so it's a minus, so it would become minus. Now e to the power lambda 1t grow unboundedly as t tends to infinity. So to stop this state to grow unboundedly, we need a control input. So that's why here you can see, to control this unstable mode, we have a control input. That means we can at least control this state x1, and we also can control the state x2. I mean, rather, or we can say that though we cannot control the state 2, it will eventually goes to 0 as time tends to infinity. That means it will eventually become a stable because of this stable mode, and this is unstable mode. That's why we need a u. So normally what basically we do, we basically convert a system matrix into a controllable uncontrollable format. That you I mean is not right now, it's not a scope of this your work, your study. So we basically what we basically do, we basically convert this system state. Let's say this is your system matrix, and we convert this system state into controllable uncontrollable format. And once you convert it into a controllable and uncontrollable format, you have to check that those are uncontrollable form, those are stable mode, those are unstable mode, are those are controllable, is there any control input associated with the unstable mode or not. If there is a no, if there is a no association of the control input, then we cannot say the system is stabilizable. But if there is association of control input for unstable mode, we can say the system is stabilizable. And stable mode, there is a whether there is a control input or not, it will eventually goes to 0. So this is basically the stabilize concept of stabilizability. This is the weak concept, weak notion of controllability. And the last thing is output controllability. So what output controllability says? So till now we have talked about basically the state controllability, right? Now we have talked about the output controllability. So in case of state controllability, we have checked this matrix should be a full rank matrix, right? If this is full rank, then system is state controllable. In case of output controllable, output is, let's say your output is y is equal to cx. Okay. So for output controllable, what you should extra do, your controllability matrix, let's say the notation that I'm using, OC, output controllability, this is basically C matrix multiplied with this controllability matrix. So what will happen? It's CB, CAB, C a square B, and C a to the power n B. If this matrix is full row rank, full row rank means if the system has a, let's say system has 3 row 4 columns, okay, then the matrix should be, the rank of the matrix should be 3. If the system has 3 row 3 columns, the rank of the matrix should be obviously 3. If the system has a 1 row 2 columns, the matrix rank should be 1. So this is full row rank. If the matrix is full row rank, then system is output controllable. Now I have just given you one example of the stabilizability, and then we'll controllability stabilizability. One example I'm just giving to you, and then we, if you do not have any queries, then we will wrap it up. Otherwise, I will take the question. So this is the system. Sorry, and this is B matrix, B vector 1 0 1, and this is C, which is 1 1 0. Okay, first check controllability, or rather say state controllability, output controllability, and stabilizability. Okay, so if you find out the C, AB, just find out the AB. What AB you will get? Multiply A with B, you will get 1 0 minus 1, and A square B, you will get A into AB. So 1 0 1. So what is the C matrix then? This is 1 0 1, 1 0 minus 1, 1 0 1. So you can see that already there exists a one row fully 0. So that means system is definitely, the matrix is this C is not full rank matrix. Also the column, also the column, this column and this column are identical. So definitely I'm not going to do any kind of determinant or row elimination. You can see by observing the matrix, you can see that the determinant is 0. That means not full rank, not state controllable, but whether it is a stabilizable or not. So what is the matrix? System state is basically 1 0 0 0 minus 2 0 0 0 minus 1. This is x plus 0 1. Sorry, 1 0 1. Right. This is u. So here you can see that this is the diagonal matrix. So these are the eigenvalues. This is unstable mode. This is stable mode, and this is also stable mode, right? So unstable mode is there is a control input. There is a stable mode, no need a control input. There is a stable mode, control input exists, but there is no need. So that means if unstable mode are controllable, and the non-controllable modes are stable, then the system is stabilizable. So system is stabilizable. Now, then third thing is output controllable. Output controllable is, let's say OC is output controllable, where you have to find out CB, C a square B, sorry, CAB, C a square B, right? So what is CB? Where is C? Yeah. So this is basically ultimately C into B, AB, a square B. So what would be? This is C110, and this is 111 0 0 0 1 minus 1 1. Perfect. Okay. This is 1, this is 1, and this is 1. So OC is full row rank. That means system is output controllable. Okay. So is there any questions right now?
No, sir.
Is it clear? Whatever the examples that I have done, that I have solved it today, is it clear to you, right?
Yes, sir.
Excuse me, sir.
Yes.
Am I audible?
Yes, yes, you are audible.
Sir, no doubt in today's session up till now,
Okay.
but I do
Okay.
have question in assignment for question 10.
Can you please tell me what is the question? I do not
That is
have a.
related with Liopanov function.
Okay. Can you please just, tell me the questions so that I can write it down and,
Okay, just a minute.
yeah.
Here in front of me. Number 4. Assignment number 4. Actually, the Liopanov function is not given, and
Hmm.
that I have assumed.
So you're
So
you're you're
after I,
basically given a system. You're basically given a system, a non-linear or linear
yes,
system, and you are asked
yes,
to find
non-linear
out the
system.
stability, asked to find out the stability or instability, what is the system stable or unstable, right?
Yes, yes, yes. I
Yeah.
will give you the system. Should I give you the question, entire question?
Okay.
Consider the following nonlinear system as given by
Uh,
x1 dot equal to x2,
okay.
x2 dot equal to
Equal to
minus x2
minus x2
minus x1 cube, minus x1 cube.
minus x1 cube. So this is the system, and you are asked to find out the stability of the system, right?
Yes, yes.
Yeah.
So I
So
have chosen Lyapunov function was not given. I have
no,
chosen
yeah.
Lyapunov function
Hmm.
as x1 square plus x2 square.
Okay. And you are not finding
So
the
we
you are not basically finding the stability of the system. So
I
let me
got the answer as unstable. I got the answer as unstable.
you got the answer as what Lyapunov functions you have chosen?
V equal to x1 square plus x2 square.
X1 square plus x2 square. And what v dot you will get 2x1 x1 dot plus 2x2
Yes,
x2 dot. Right? So
yes,
this is
yes.
2x1 x2 plus 2x2
Into bracket
here x2
minus
minus
x2
x.
plus x1 cube. Yes,
Yeah. So x1 x2 minus 2x2 square minus 2x2 x1 cube.
yes.
So this is the result. So how can you say that this is the I mean you are unstable? How can you say this is unstable? First of all, what is the
For example, I have chosen x1 equal to minus 1.
hmm,
So x1 cube will be minus 1 and
hmm.
minus and minus will become plus. So it is positive definite. So V dot is
So you
positive.
have to
So the system
so
is unstable.
yeah, just let me explain and just I'm just interrupting you over here. So for make this is unstable, that means you you have to for make this system stable, you have to show that this v dot is at least less than or equals to 0 for stability, right?
Yes, yes,
Uh, Now for instability, definitely it has to be greater than 0, right?
yes.
So you have to check every x1 and x2 first of all, whether the x1 is negative, x2 negative, x1 negative, x2 positive, x1 positive, x2 positive, and x1 positive, x2 negative. Every cases you have to check that whether every cases you will get the v dot is greater than 0 or not. First of all, this is undefined case. Undefined case means you cannot directly say that the system is positive definite or negative definite because you don't know what should be the value of this. Let's say I'm taking x1 x2 both positive. If I'm taking
Hmm.
x1 x2 both positive, that means this term is positive term, this term is also positive term, and this term is also positive term, right? Right?
Yes, yes,
Yeah.
yes, yes.
So all these three terms is positive term. Now, how can you say that this term is less than this term? If this term is less than this term, then this is less than 0,
Hmm.
right? That means
Right.
system is stable.
Hmm.
If this term, if the first term, if this term is greater than this term, that means
Greater than 0.
it's not greater than because it has to be like the term one. This is, let's say, term I'm just writing down as a, let's say, t1 minus
T1.
t2 minus t3.
Hmm.
So if t1 greater than t3, definitely t1 minus t3 is positive,
Yes,
and then this term has to be less than 0, less than t2 to make this system v dot negative definite, right?
yes,
So
yes.
that means you can't say anything about this. From here you can't say anything about the stability, about the stability of the system. That means the system is undefined. Does that means we cannot find out the Lyapunov function so that we can find out the stability of the system? No, that is not the case. So in Lyapunov class, I have already shown similar kind of scenarios. So this is the system over here. Okay, so first I have chosen, this is the Lyapunov function, half x1 square plus half x2 square. And using that, what I get this term, this x1 dot x2 dot, this term I get, x1 x2 minus x1 cube x2 minus x2 whole to the power 4. So if I use this Lyapunov function, my system is undefined. I cannot say anything about the stability of the system. But now I change the Lyapunov functions to this one, 1/4 x1 to the power 4 plus half x2 square. So the choosing of Lyapunov function is like that. The v of x should be positive definite function, and it should be 0 at x equals to 0. This is basically the concept. This is basically the condition to find out the Lyapunov function.
Leo-
So definitely here I can see that my this one is positive, this one is positive. So this is a positive definite function, and when x1 and x2 both equals to 0, then v of x is 0. That means this is can be considered as a candidate Lyapunov function. Now if I find out the v dot over here, and you will see that I get this term minus x2 to the power 4 is less than 0. That means at least I can say the semi-definiteness of the, the at least stability of the system. At least I can say that the system is stable in the sense of Lyapunov.
Mhm.
It is not asymptotic. I cannot say anything about the asymptotic stability. For that, I have to check whether any other Lyapunov function exists or not, by which I can show the asymptotic stability. But here I am not saying that system is asymptotically stable. I'm just saying the system is stable. So that means my this Lyapunov function doesn't work, but this Lyapunov functions work. So in your case, there may be your this Lyapunov function does not work because you are getting an undefined solution. So you have to choose another Lyapunov function so that we can get a stability of the system. Okay, so that's why it is called the checking of this stability using the Lyapunov function is not a necessary condition. That means if you cannot find any stability using this Lyapunov function, you cannot say that okay, the system is not stable. No, this is basically a sufficient condition. If you get, that means you can say the system is stable. If you not get, that means it possible there exists another Lyapunov function by which I can find out the stability of the system. Okay. So maybe in your case, this Lyapunov function is not correct one. You have to choose another Lyapunov function. You have to search for another Lyapunov function and check whether you can find out the stability of the system or not. Okay.
The variables are having even powers. Am I correct? That
Yeah,
means
variable
if
has
you
to
have
be
chosen x1 raised to 4.
variable has to be even powers exactly, because you can't choose x1 cube plus x2 square, because
Yeah.
if you choose let's say v of x equals to x1 cube plus x2 cube. So that means if x1 is negative, that means this one
Negative.
is negative. So that means my condition is not satisfied. So this has to be a positive definite function. So you have to check whether there exists any kind of system states by which, sorry, any kind of Lyapunov functions by which I can find out the stability of the systems or not. If you find that system, then it is okay, because there are also another theorems also exist. I mean, this Lyapunov theorem is not a sole theorem to find out the stability. There are all another theorems are exist in the literature, which you are not basically studying. You are not going to study it in this course. This is the
Okay.
advanced course level. So first, you check
Yes.
that there exist any other Lyapunov functions or not, because this is not basically surely this is not working for this case.
Because even in the solution, they have taken some different Lyapunov function.
Okay, so you are given already
Let
a
me.
solution.
The solution is given
Okay,
provided
okay,
by
okay,
NPTEL
okay,
itself.
okay, okay,
So let me just read out that if possible. Just give me a minute.
okay.
That is what my basic question was, that how we can choose the Lyapunov function. Basic is x1 square plus x2 square, so I have
This
started
is
with that.
basic. Definitely,
But
this is the basic one, but it is not
uh,
always the case. Sometimes, like
uh,
in previous case, like in case of uh, this pendulum, you can go
mhm,
and check my note. In case of pendulum, I have
mhm,
not chosen any kind of x1 square x2 square. I have chosen two energy functions. This is the potential energy
mhm,
and this is the kinetic energy. So this is also a positive function. So you have to choose
mhm.
any positive function. That has
Yes. In
function has to be
solution,
positive
they,
one.
okay. In solution, they have taken x1 raised to 4 plus x1 square, 2 plus 2x2 square.
Sorry, v of x is
x1 raised to 4
x1 raised to a 4
plus x1 square
plus x1 square
plus 2x1 x2
plus 2x1 x2
plus 2x2 square.
plus 2x2 square. So I'm not sure you can choose this as a Lyapunov functions or not, because I'm not sure, because according to my knowledge, this term is not exactly positive definite function,
Mm,
right?
mhm,
Because you, if you say like x1 is positive and x2 is negative, or vice versa, then
mm,
this term is negative one. In that case, you
mhm,
can't say completely about the whole term is positive definite functions or not. This would be, this function would be, this v of x is always greater than 0 if x1 is positive, x2 is positive, or x1 is negative and
mm.
x2
Both are
is
negative.
negative.
Mm,
Then this is the positive definite function, right?
mm,
But there is another condition should be there. The v of x equals to be 0 if and only if x equals to 0. That means x1 and x2, if both equals to 0, then we,
mm.
the v of x should be 0. But in that case, I think this will happen, because both is 0. If x1 0 and x2 0, both zeros, then v of x is 0. So second condition,
0.
this condition is happening, but this condition happens
Mm,
only these two scenarios.
mm.
If any
But this is
one
the
of them.
solution given by NPTEL. This
Okay,
solution
so
is given by
okay,
NPTEL.
so I'm just confused about this term, because I'm not sure whether I mean,
So
whether I
actually, that
can.
is why I have asked you in question and answer forum